Hello everyone, my name is Horace, and in this video we're going to be going through LeetCode number 169, majority elements. For this problem, we're given an array which is called nums, and it has a size of n, so there's n elements in the array. We have to return the majority element. The majority element is defined as the element that appears more than the floor of n divided by 2 times. And we can assume that the majority element is always going to be present in the array nums. So really we just have to find the element that occurs the most in the array. Well, we know if the element appears more than half of the total elements, it's going to be the most frequent element in the array. Well, one approach would be to keep a dictionary with the frequency of each of the element occurrences. So in this example, we have 2 occurring 4 times. So the dictionary would have 2 mapped to 4, and we have 1 appearing 3 times, so we have 1 mapped to 3. And we can just return the maximum of the dictionary frequencies, and in this case it would be 2. Now this is a valid approach, and this approach is going to take big O of n time and big O of n space, since we only have to traverse once and then twice to find the maximum in the dictionary. Well, we can actually get the space complexity to be big O of 1 by using something called Moore's voting algorithm. Well, to implement the solution using this approach, we have to keep track of 2 things. The first is going to be what is known as the candidate, and this is going to be the element that we return. And we also have to keep a count. And this is going to be initialized, let's say, to none. And this is going to be initialized to 0. We know that since the majority element is going to occur more than half of the times, we know that the count of the majority element is strictly greater than all of the other elements combined. So for example, if we take a look at this example, we see that there are 4 occurrences of the majority element 2, and there are 3 elements that are not the majority. And these 3 elements happen to be the same, but let's say they were different. For example, this could be a 3 and this could be a 4. And we still have the property that the majority element count is still strictly greater than all of the other elements combined. So in this case, 4 is greater than 3. Well, let's say we start and initialize this to be the candidate value. Well, now the candidate is 2 and the count is 1. Well, we can iterate through this array, and if we move the pointer here, well, we still have the same candidate, and that means if we have the same candidate, we want to increment the count. So let's say the count is 2 now. Then we keep going through. Well, now the element that we're looking at in the array is 1, and 1 is not equal to the candidate, which is 2. And since the count of the candidate element is not 0, meaning that we have still elements in the majority, then we just want to decrement this, and we'll get 1. But the candidate is still going to remain 2. Then we keep it going. Then we're at 1, and 1 is again not equal to 2. So we go ahead and decrement the count value. Then we keep the array traversing. Now we're at 1, and 1 is not equal to 2, and the count is equal to 0. So since the count is equal to 0, what we're going to do is we're going to basically update this to be 1 and then update this to be 1. So now this is the majority element in the array thus far, and we can see that this is true. If we just look at this portion of the array, we see that there are 3 1s and 2 2s. So 1 would exactly be the candidate, and you can kind of see how this algorithm is working. Then we keep moving forward. So now we're at 2. 2 is not equal to the candidate, so we decrement the count to be 0, but we do not update the candidate. And if we were given something like this, it would actually be an invalid array since there is no majority element. And then finally, we are at the final elements in the array, which is 2. 2 does not equal to the candidate, and the count is 0. So first thing, we update the candidate to be 2, and we update the count to be 1. And then now that we've reached the end of the array, we can see that we have a candidate value, and this is the candidate value that we're going to return. And lucky for us, it's exactly the candidate 2 because we have one count more than all the other elements combined. So hopefully this algorithm makes sense. It might take a little bit to kind of understand what is going on with the incrementing and decrementing of the count. But when we return, the count really does not matter. It's only the candidate that matters since this is the element. And just to reiterate, the time complexity is big O of n, and the space complexity is big O of 1. So with that being said, we can go ahead and write the code on LeetCode. Okay, we're on LeetCode and we can begin writing the algorithm. So as I mentioned previously, we want to define a candidate, and let's just initialize this to none, and also a count, which is going to be 0. We want to iterate over the array, so for num in nums. And then we want to check every time the count reaches 0. So every time the count reaches 0, what did we do? We updated the candidate. So if count is 0, we want to just make the candidate equal to the current element that we're looking at in the array. Finally, we just have to increment or decrement the count. So when do we update the count in terms of incrementing it? Well, we increment it when the num is equal to the candidate. Otherwise, we decrement the count. And this is pretty much it. We can just return the candidate, which is the element, and we can submit the code. And as you can see, the code is accepted. So we can take a look, and it's very efficient in time and space. This is the optimal solution, running in big O of n time and big O of 1 space. So hopefully this video helped you and you learned something, and I'll see you soon.